All right, let's jump right in. We're about to pull back the curtain on one of the most powerful and honestly elegant tools in all of signal processing. We're going to learn how you can literally draw the exact filter you need.
Yeah, you know this sound. It's that awful 60 hertz hum you get from electrical noise. It can totally ruin a perfect audio recording, this constant, low-level buzz that just sits under everything.
So, how do we get rid of it? Well, the answer is a digital filter. But, and this is the important part, it's not about memorizing a bunch of crazy equations. It's about understanding a simple, visual way to design these things, kind of like placing pins on a map. So first, let's meet our main tool, the digital filter itself, and more importantly, the map we're going to use to control it, which is called the Z-plane.
You know, every filter has this core recipe. It's called a transfer function. And when you boil it all down, it's basically just a fraction, with one polynomial on the top and another on the bottom. That simple recipe dictates literally everything the filter is going to do. Now, here's where it gets really cool. We can actually visualize that recipe on this map, the Z-plane. Just think of this circle, the unit circle, as representing the entire frequency range of our signal. The low frequencies, they're right over here on the right side, and then they wrap all the way around to the highest frequencies. And those polynomials from our recipe, their roots give us our controls. The roots from the top part, the numerator, are called zeros. We mark them with the little circle, and their job is to cancel out frequencies. The roots from the bottom, the denominator, are our poles. We mark those with an X, and they boast frequencies. That's it. Those are the only two tools we need to build pretty much anything.
So the real secret here is getting an intuition for how placing these poles and zeros on the map shapes the sound. This is where the magic happens. Okay, picture this. Imagine a little point traveling all the way around that unit circle, testing out every single frequency as it goes. The filter's power, its gain, at any one of those spots is just a simple ratio of distances. You just multiply the distances from your test point to all the zeros, and then you divide that by the product of the distances to all the poles. So think about it. What happens when our little traveling point gets really close to a pole? Well, that distance in the bottom of our fraction gets super, super tiny, right? And what happens when you divide by a really tiny number? The whole thing just shoots sky high. And that's how we create a big, resonant peak in the sound. And of course, the opposite is true for zeros. If our point gets really close to a zero, that distance in the top of the fraction becomes tiny. And a tiny number on top means the whole thing gets dragged right down to nothing. It creates this super deep valley, or a notch, that can totally silence one specific frequency. There is a fantastic way to visualize all of this. It's called the rubber membrane analogy, and it is by far the best mental model for what's actually going on here. It's just brilliant. The poles are like tent poles, literally pushing the frequency response up into these mountains of gain. And the zeros, they're like pins, tacking the membrane down into these deep valleys of attenuation. The actual height of that rubber sheet right along the edge of the unit circle, well, that is your filter's frequency response. All right, so with that physical intuition in our back pocket, let's put it to work. Let's actually build a filter to finally kill that annoying 60 hertz hum we started with. We're going to design what's called a notch filter in just 4 simple steps. First, we find the exact spot for 60 hertz on our unit circle map. Step 2, to kill that frequency, what do? We plant a zero right on top of it. But wait, we're not quite done yet. See, just placing a zero works. Kind of. It definitely creates that deep notch we want, but it also creates a new problem. The valley it makes is really wide and sloppy. So yeah, it kills the 60 hertz hum, but it also messes with all the frequencies nearby, which would just distort the audio in a different way. And this is where the pole comes in to save the day. By placing a pole just behind the zero, its push-up effect counteracts the zero's pull down everywhere except right at the notch. It's amazing. This one little addition transforms our filter from a clumsy, blunt instrument into a surgical tool. We get this incredibly sharp notch that targets only the noise and leaves everything else completely untouched. And the result? Crystal clear audio. The problem is solved, not with complicated math, but by using this really intuitive, almost geometric design process. So this simple idea, this game of placing poles and zeros, it isn't just for fixing noise. It's actually the fundamental building block for pretty much every kind of digital filter you can imagine. For instance, what if you put a pole near the low frequency part of the circle? Well, you're propping up that rubber membrane for all the low frequencies, letting them pass right through, while the rest of the membrane just kind of sags. You've just built a low-pass filter. That's exactly how a subwoofer crossover works.
Now let's do the opposite. Let's put a 0 at that same low-frequency spot. Now you're pinning the membrane down, blocking all the bass and letting only the high frequencies get through. And just like that, you've designed a high-pass filter, the kind you'd want for a set of tweeters.
What if you want to isolate just one specific group of frequencies in the middle? Easy. You just use 2 poles to build a focused little mountain of gain. This lets only a very narrow range of frequencies pass through, which, by the way, is the exact principle behind tuning into your favorite radio station.
So when you really boil it all down, what's the big takeaway? It's that filter design can be an intuitive art form. You're literally just placing peaks and valleys on a map to sculpt whatever sound you want. Poles push things up, creating peaks. Zeros pull things down, carving out valleys. And how close you put them to the edge of that circle, that just decides how dramatic their effect is.
And that leaves us with a really fascinating thought, right? This isn't just about making the standard filters we already know. If you have this intuitive control to sculpt a frequency response with any mountains and valleys you can imagine, what new creative ways could you shape sound or data or any kind of signal? The possibilities are really endless.